Okay, lesson 7. The very start, fill in the blanks. So this is going to be about, again, factoring polynomials and relating it to the graphs of them now. So it's really just kind of building off that last thing we did. We're skipping lesson 6. So fill in the blanks. This is just reminding you that all these words are the same. I feel like we made a really good point about this in grade 11 and in grade 12 already. So we know that zeros, x-intercepts, roots are all the same number. They're all the whichever way you want to think about them most. I think about it graphically usually in my head, so I like to think they're all the x-intercepts, they're all the points where the polynomial hits the x-axis. That's the way I like to think about it. Okay, unique factorization theorem. So we're getting lots of theorems in this unit, which is kind of nice. I always like a good theorem. And this one is actually a pretty important one. This is one that I think we can probably guess at from grade 11, but I don't know we ever say explicitly until now. So here's the unique factorization theorem. This theorem states that every polynomial function, usually these things are common sense, but it actually takes somebody to prove them, so they become pretty famous. Every polynomial function of degree n greater than or equal to 1 can be written as a product of a leading coefficient c and n linear factors. So every single polynomial can be written in this way, is what it's saying. You can have some kind of common factor and then a set of factors. And every single factor tells you what the x-intercepts are. So hopefully you're looking at that and you're thinking to yourself, does this seem right? I thought we talked about there's quadratics that don't have any roots. Remember we have some kind of quadratic that only goes up. How could we possibly write this polynomial in this way? In grade 11 we say it's not possible. We can now, we could do it, well, not really now, but it is theoretically possible to do it, just they're going to end up being imaginary roots. So the things in these brackets are going to end up being imaginary numbers. So it's not necessarily integers or real numbers. Sometimes they might be imaginary. But it is always possible to write these things. This does have actual solutions, just they're imaginary. So this theorem has two really important points for the polynomial function of degree n greater than or equal to 1. Every polynomial function can be written as a product of its factors and a leading coefficient. So that's number one. And there's actually, it doesn't say it, but I think it can be, I don't know why they didn't write uniquely. I might be mistaken on that, but I'm pretty sure it can be uniquely written. Like if you are fully factored, there is only one final form a polynomial can get to when you're fully factored. I'll have to double check that after this video, but I'm pretty sure that's the case. Well, the order of these things could be different, like this bracket and this bracket could be flipped, but there is only one possible end state for a polynomial when it is fully factored. If you pulled out all the common factors and you followed the right form, then there should only be one unique end state for these things. There isn't, alternatively, it seems like maybe you could have factored it a completely different way and gotten a completely different answer, but no, that should not work. So they can always factor it, and every polynomial has the same number of factors as its degree. So if it's a degree 2 polynomial, you end up with 2 brackets. You have 2 factors. If it's degree 3, you'll end up with 3. If it's degree 7, you should end up with 7 brackets. Because every single one is a single value of x, so when you multiply it 7 times, you'll get to your 7th degree function then. So there's that one, but now here's that caveat I was telling you about. These factors may be real, they may be complex. Complex is another word for imaginary, which means it involves a root of a negative number, which we can't do with our normal numbers. And it may be repeated. You could have the same one. You could have like an x plus 1, x plus 1, x plus 1, x minus 2, something like that. So it could be that, but if you expand it out, then there's the same number of factors as its degree. Should be common sense. Okay. The graph of this function is shown. The polynomial has integral zeros. All the zeros are whole numbers. That's what integral means. It means integers. That's our fancy Z word, Z symbol. State the zeros of this polynomial. To me, that looks like -2, 1, and 3. So the zeros are at, I'll say zeros, at -2, 1, and 3. State the factors. So I could write this polynomial. Do we know what degree this is going to be? It goes from down to up, so it has to be an odd degree function. And it looks like it's going to be third degree, and indeed it will be. So this one can be written as x plus 2, x minus 1, x minus 3. Maybe with something in the front. Write this polynomial in factored form, and that's just this. And there could be an a value in the front, but there's no a value here. I don't think there's any exception to that. I'm pretty sure that's the rule. Whatever coefficient there is on the leading coefficient ends up being the a term. Or at the very least, if it's 1, it has to be 1, I think. Okay, using a graphing calculator, use a graphing calculator to sketch this in expanded form and factored form to verify. So actually, let's check this. This is quite an assumption. We're not sure if we trust that yet. Let's use a graphing calculator, see if it turns out exactly right. And then we can expand it out as well. I don't have the expanded form, but I can do it fairly quick. In the first ones, it's x squared. They add to positive 1. They multiply -2. So it's going to equal x cubed minus 3x squared plus x squared is minus 2x squared. Minus 3x minus 2x is minus 5x plus 6. So let's actually check those two things. Check number 1 and check number 2 and see if it actually does graph the way it should. So pause the video. I'm not going to check. I'm pretty confident that it will work out right. Maybe I did my expand wrong, in which case, let me know. Okay, moving on. This is actually the last question. Very short lesson, this one. Use a graphing calculator to sketch the graph of a polynomial function p of x equals -x cubed plus 4x squared plus 7x minus 10. Okay, so let's make a little graph of it. I'm going to bring up my Desmos. -x cubed plus 4x squared. So use your graphing calculator and try and draw a little sketch of this. How high do we want to go? It goes pretty high. It goes down to like -13 up to 20 something. So we'll call the top 21, we'll call the bottom -21. And we have zeros at -2, +1, and 5. We have one intercept, one minimum, sorry, down here. And a maximum up here. So we get something like that. Use the graph to state the x-intercepts. So x-intercepts at -2, 1, and 5. Write this polynomial in factored form. So p of x is equal to x plus 2, x minus 1, x minus 5. Is that right? This is where it becomes really important to remember that there's always some kind of coefficient that goes in there. And that coefficient is, in this time, it's just going to be -1, I believe. You might have to, in some more complicated ones, you might have to solve for that, but since we have it here, I'm pretty sure whatever the leading term is just goes in there. I would actually check that. Let me actually write that in just to double check. Sorry. X plus 2, x minus 1, x minus 5. Yep, same. Yep, so whatever the a value ends up coming down and becoming the coefficient, the common factor, sorry. Well, either coefficient or common factor in this one as well. If without that, it's actually going to be going the other way around. It's still going to hit all these x-intercepts, but it's going to be flipped upside down. And it very well could be different things. You might have to, in some questions, maybe this is coming up in the later units, you might have to actually check using some other point on the graph. So you could sub in the values of this point. You could put that as an a value. You could sub in this for x and y, and you could solve for a, just like we did with quadratics. So you might have to do that. So circle the correct alternatives. The left arm of this graph, the left arm, this is kind of the extreme value as you go to the left, it is falling. Well, I mean, it's kind of, it depends which way you're looking. If as you're traveling to the left, it's rising. As you're traveling to the right, it's following. Usually I like to think of these things as it's going to the right. I would say it's a decreasing function at this point, but it's going up. So I think they actually mean that. It's going up. The left arm is going up. The right arm of it is going down. The degree of the polynomial is odd. In case you forget, this is a third degree polynomial. The degree of the highest term, the degree of the first term, if it's in the right order, is 3. And the leading coefficient of this polynomial is negative. And these are general rules. You should be able to figure out these pretty easily just from this graph. So first of all, we're looking how many times it crosses the axis, although that might not always work. But it works in this case. It definitely works for the odd ones. So this is a third degree polynomial, or you look how many times it changes direction. It should change direction 1 time less than the degree. So 2 changes of direction, that's actually the more reliable method. Because x-intercepts, sometimes it can be weird. Like I could have drawn a cubic like this. In which case, it's going to have only 2 x-intercepts, but it's a third degree polynomial. This one right here is going to be the same one twice. If that was at +3, it would have an x minus 3 squared as a factor. So the x-intercepts aren't always reliable, but the change of direction is reliable. So whatever the number of changes of direction are, that's always 1 less than the degree. So a parabola, degree 2, has 1 change of direction. Cubic has 2 changes of direction. So that's why every cubic function will always either go from rising to falling or from falling to rising. It's going to change direction. Every odd degree polynomial, actually, because it's odd, these two are going to be different. If this was even, these two are going to be the same. It could either go from rising to rising or falling to falling. And the order it does it is based on the leading coefficient. So this one leading coefficient is negative, which means it ultimately is going down. And if you go really far somewhere in the past it must have been going up then. Okay, that's it for this short lesson, only 15 minutes long. I'll do the homework. It says assignment to be done in partners. There's only 3 of you guys. If you want to work all together, you can. If you like to work individually, you can do that as well. Good luck.